Okay, now this is not my first go at this, so if you'll forgive me, I can put that away, bring this up. Now there's this is the article I can keep mentioning, or have mentioned, that describes how the Hermite interpolation between 2 points works. Okay. Now it turns out that his labeling is not the same as mine. So I've written down my labeling. Basically, oh no, I am using his labeling, aren't I? That one, third. Okay. Alright, so the labeling's the same. And I don't need this. I don't want to look at this because it'll get us confused. It's all the same. I'm using all the same names, and I've set it all up in the program so that we can just watch. Oh, well, one thing I have to point out. This here, the formula, alright. Now, see, that's incorrect. This one is different. Oh no, that's right. H2P2. Here's mine. H2, okay, it's the same. Okay, now the formula for figuring out the point has to do with these vectors, P1, P2, T1, and T2, which are in the picture up here. Okay, now this formula says to multiply at each point for each position at T or S or whatever, H times the vector. Okay. Now I'm not doing multiplication. I'm using the variable substitution, which I'm just going to show you and point out. As proven here, that the variable substitution for this case is exactly the same as multiplication, because the class I vector implements itself this way. Okay, the point is given by this expression. I'll show you the code. Have it ready here somewhere, just for this purpose. Now, what am I doing way down there? I vector impl here. It's point 1, that's the first point passed in, plus t times the difference between 2 and 1. Okay. P1 plus t times 2 minus 1. Now, what I've done is I've used 0 for P1 everywhere for my algorithm. Right? So I'm basically just using the magnitude and direction, but not position of these vectors. So P1 is 0. If P1 is 0, then this expression reduces to P equals T times P2. So substituting one of these H's in is the same as multiplication. Okay? Alright. So I've written down these 4 functions. This hack, by the way, is a thing I invented. This does cubing and squaring. It's just a cutesy little thing. I always like to be able to put hat, instead of pow or some dumb thing like that. although I have to make a cast to this special count structure. So that's the first one, H1, right? Can we see those together? Sort of. I have to make one of these small. Bring this this way. There we go. Okay, 2s cubed minus 3s squared plus 1. 2 minus 2s cubed plus 3s squared, and h3 s cubed minus 2s squared plus s. And then the last one, s cubed minus s squared. Alright? So we can refer to these anytime we like, and those are the actual functions being used. And in the end, the expression will look like this. Now, let's go to the screen here. P1 and P2 represent the points from where we start and where we will end up. Okay? T1 and T2, as in that diagram, disappeared now, are tangents, okay, and their magnitude, the length from here to here, will determine the curvature of the curve. You know, if it's a short length, it won't be as curvy as if it's a long length. I can make this big now, by the way. I fixed the bugs. Oh, you know what I did? You know what happened with that little sprite thing? I should have realized this. But whenever I switch to full screen mode, right? Because it's based on a WM timer message, it dies because when I switch to full screen mode, I destroy the window completely, right? So I'm not going to get any more WM timers. And I thought, well, maybe I can call something back, you know. But then I figured that it'd be a lot easier to just make my own timer, and that's what I did in the coordinate system here. It's more of a general purpose thing, but for now it's in here. Where is it now? Animation timer. It's a thread, okay? And all it uses is one of those waitable timers. I use a manual one, and you can say start ticking and give it a value for the timer and stop, and so this thing is constantly signaling itself, and when it gets a signal to itself from itself, it first of all, initially when you create it, it takes note of the main window thread, okay, because this creation occurs in the main thread, right? I haven't started the thread yet. This is the constructor. So it knows what the main window's thread is. The thread is, but if the window dies, the thread doesn't change, right? The window may die, but the thread won't die, the main thread of the program. So then it just, when it gets signaled, it calls, there's a thing called enum thread windows, which I used before, you know, to, for my tray thing, right? That when I wanted to hide the windows of a program. Enum thread windows of the main window thread, and then this thing just calls a callback for every top level window in the program. There might be a dialog up, who knows. But I create a unique WM app message, which I call unique WM app message, and post that unique message that comes in as lparam here to every window in the program. I don't care which one's the main window, I don't bother with it. Most of them won't do anything with that message, but one of them will. And in the WinProc, there's just a call when it sees a message, unknown message, near the top of WinProc. That's WM create. Then it calls this function is asking if it's the timer message. And that is implemented by asking the timer if that's its message, true or false. If it is the timer message, then it calls the graphs on timer. Now, I mean, the graph could have done that during this call, but this is the way it was written before, right? If message equals WM timer, WM graph timer or something, then we call that. So I just left it. So now that timer will never die. So I can go to full screen mode and we can run the demo. And I've used color coding and so on to try to help clarify what's going on. And from what we discovered, or what I discovered recently about this adding functions together, has simplified things tremendously. It's very easy for me to do this demo now. So the way I've set it up is, well, first I'm going to draw these vectors. First one, a bluish color. How about this? Now this one gets filled in automatically for me for this demo. Okay, so this is the T1 vector, and this is the P1 vector. Okay, and this one I'll make a kind of a pinkish color, but not exactly that pink. Close, like a redder pink, like this. Okay, so this here vector is T2, and this vector is P2. Okay. Now the way the formula works is by multiplying the various vectors by different amounts that change between the period of 0 to 1, t equals 0 to 1. Now the first demo, what I want to show you, what you're going to see is the effect of the first term here. H1, which is this curve, it starts out at 1 and goes down to 0 during the interval. And so since that's multiplied by this vector, that will have the effect of, starting the position will begin at 1 times this vector, which is this vector, and reduce to 0 at the end. So I do Control T, it should start. So now it's doing that. That is the first term, H1 times P1. Okay. No mixtures or anything. Now the next thing that follows this in the series is the third term, H2 times P2. h2 is the opposite basically of this curve, starts at 0 and ends up at 1, and is multiplied by the p2 vector, so that will have the effect of moving the ball from 0 to p2. Okay? So there you go. That's the effect of this term. Because it's increasing. I should have made this one longer, but whatever. At the end it's 1, and so therefore that leaves you at p2. Now the next demonstration is what happens if I combine the first term and the third term together. Well, we know that after the period from 0 to 1, this one starts out at p1 and ends up with nothing. And this one is doing what it's doing now, starts out with nothing and ends up at p2. So the combination of those two should take us directly from p1 to p2. And that's what those terms are for. Okay, here it is. Now this is the sum of the first and the third term with nothing to do with the tangents. Now how do the tangents affect this? What we require, okay, is that the curve be tangent to this vector at this point in the journey, okay, at t equals 0. Well, if you look at all of these curves at t equals 0, in terms of their derivatives first, this one's derivative is 0, okay, and same for these two. The only one with a non-zero derivative is this h3, right? So at t equals 0, if we had all these things together, or even just 1, the direction of motion for a little while is going to be along the t1 vector. It has to be, because all of the other derivatives are 0, and so there's no d distance d p1 that's not changing, or with respect to p2, or with respect to this thing. The only one that is actually changing at t0 is this one, and so therefore the direction of motion will be along this tangent. Okay, that's a guarantee. However, eventually this thing smooths out, right, and it starts to die, and it's not very big anyway. And this one's slope becomes quite high, negative, and so it will tend to move back and follow this line again, and then they're both 0 here. So if I combine 1 and 3, which is what I'm going to do next, we should see it come out a little bit and wind up back in the middle. So there'll be a pull along the tangent, and then it'll wind up at the end to the middle. Okay? And there it is. So this here motion is now the sum of the first two terms, t1 h3 times t1 plus h1 times p1. So this here, this term has the effect of causing this to be tangent at this point to this line, right? And pulling it out a little bit, pulling it out a bit, and eventually just you can see that the slope of both of these is 0 when they reach the end. So they have no effect on the motion or position near the end of the journey. Okay, now the next test is to do the same thing with P2 and T2. So H2, P2, and H4, T2. Now in this case, at the beginning, there's no, as I said, there's no motion. There'll be a slow start. But eventually, this pink one, this term, becomes steep, and so we should see an increase of speed, right, along this P2 vector. But then eventually this H4 starts to become big in the opposite direction, and so there'll be a pull away from this vector. And then in the same way that these things combine to make this tangent here, that happens at the end here, because this one slope at the t equals 1. The only curve that has a non-zero slope is H4. This one has a slope. This is 0, 0, 0, 0, 0. So the direction of motion at t equals 1 will be towards, along this tangent. So step over to that one so you can see, and that's what's happened. It picks up speed, eventually dies. The pink one eventually died out. Well, it's becoming 1. This is the one that is drawing the position to here. But as far as the curvature and direction of motion at the end, that's due to this one here, because it's the only one doing anything at the end, keeping it moving. So now, the last step is to just add all 4 together. And there we go. That's what we get. This one's not very curvy, but you know, you get what you get. That's a smooth curve between 2 points, turns out. Okay, now I could fiddle around and try different experiments, but you get the idea, and you can always download the code or do it yourself and try different values. Well, I can try another round of this. It will not work. Let's get some weird thing here. I don't know. Do something weird. So a long vector. There you go. Now that's pretty curvy. That's a nice looking curve. And apparently that's the only solution with a cubic. Well, I don't know. That's what I read, that it's the only solution, but I'm not sure if they mean the only curve, because I know that you can change the behavior of these things, but with scalar quantities. So maybe you can make the bending more pronounced, but it's the same. The result is just like a scalar times this curve, if you know what I mean. Okay, so I think this will do. I'll upload this one. And if anyone wants, well, this program's not done. Well, the bugs are starting to disappear, as you can see. One of the things I got rid of were all those ones, the memory leak from the type, the RTTI type name function that has a memory leak. And the way I fixed that is I simply just stopped using it. It turns out, in fact, I did have a real memory leak. Eventually I got one, and I didn't know about it until I got rid of the STL leak report. Alright, see you next time. And then the next step is, by the way, we're not done. We haven't made a spline yet. We've made in two ways, we've made a Bezier type curve. A spline now is we're going to put them all together and normalize the speed. And I have a way to do that, and I might use that or a different method, but I probably will use the one I have already. It's very simple. It's just based on well, you'll see when we get there. Okay, see you. Bye.